In this lesson, we're going to go over antiderivatives and indefinite integrals. So in the first half of calculus, we were finding the derivative, and now we're going to do the reverse of that, which is finding the antiderivative. Some examples of how an antiderivative is used would be a physicist who knows the velocity of a particle, which is the derivative, might want to find its position at a given time. So in order to go from a derivative to an original, we would take the antiderivative. An engineer who can measure the variable rate at which water is leaking from a tank. Again, rate means derivative. You want to find out the amount leaked, so that is the antiderivative. And a biologist who knows the rate, again, rate is derivative, at which bacteria population is increasing, might want to find out the size of the population at a certain time, and again, the amount of something, like the amount of the population, which would be the antiderivative. So what an antiderivative is, it's the backward operation that goes from the derivative of a function to the original function itself, in addition with a constant. So there's two types of notation that we could see. The one on the right here we're kind of used to seeing, where f prime is the derivative and f is the antiderivative, and notice that they are lowercase. But you can also have a lowercase f that refers to the derivative, and the capital F would refer to the antiderivative, or the original function. So just be aware of the notation. Now if we're trying to find the derivative of capital F of x equals 1/3 x cubed, the derivative would be lowercase f of x, so not capital F prime. And if we take the derivative of this, we're going to get x squared. And same thing for the second example. If we take the derivative, this would be lowercase f, and again, we have a derivative of x squared. So we can see that we get the same exact derivative with two different equations. Now the equations are very similar. They are related to the parent graph, but the second graph has a plus 100 on it, so that means it's going to be moving up 100. So this is very important. When you're taking a derivative of something that has a constant added to the end, whether it's added or subtracted, the derivative will be the same. So every derivative of all of these functions is going to be, in this case, x squared. If I take the antiderivative, I'll get this 1/3 x cubed, but I could have different constants attached to it. So when we take the general antiderivative, we're always going to attach a plus c. Now a plus c is very important. It stands for an arbitrary constant. So that kind of envelops all of these different constants that it could possibly be. So first, before we start looking at how to actually kind of go backwards, we're going to think about being backwards a little bit. So we want to find the most general antiderivatives. So here we have f of x equals sine x. So this is actually the derivative. So if the derivative is sine x, we want to find what the original function would be. So basically we're thinking to ourselves, sine of x is the derivative of what? So that would be the derivative of negative cosine x. And then we have to attach a plus c. So again, number 2, f of x equals 1/x. So 1/x is the derivative of what? So the original function would be the ln of the absolute value of x plus c. And then on the last one, the derivative is e to the x. So what is e to the x the derivative of? That's the derivative of e to the x. And then we need a plus c. So for certain ones, we can think about, we know what we're looking at, the derivative, so that's the derivative of what. But when we have a power function, we're going to have to reverse the power rule. So here we have a function y equals 5x to the 4th, and we know how to find the derivative. We know that the derivative is going to be 20x cubed. But the reason that it is 20x cubed is by using the two steps of the power rule. The first step is to bring the power in front and multiply it to whatever's in front. So if I'm starting with 5x to the 4th, I'm going to bring the exponent down and multiply it. So 4 times 5x to the 4th, which is going to give me 20x to the 4th. So that's where I'm leaving off. So I have 20x to the 4th, and then I'm going to reduce the power by 1, which gives me 20x to the 3rd. So even though we technically are doing two steps, we kind of do this as like one thing in our brains, but it's important to see the two steps for when we reverse this process. So to reverse the process, we're going to reverse the order of the two steps and reverse the math within each step. So the first step in the reverse process will go with the second step of the regular process. All right, so the second step is to reduce the power by 1. So the first step is going to be the opposite of that, which is increase the power by 1. So here we're starting with the derivative. So the derivative we said was 20x cubed. So we're going to take 20x cubed and we're going to increase the exponent by 1, which is going to give us 20x to the 4th. Right? Then the second part of this process refers to the first part of the original. Right? So the first part talks about bringing the exponent down and multiplying it. And the reverse of that would be bringing the exponent down and dividing it. So we're going to divide the new power. So we have 20 over 4 x to the 4th. And when we do 20 over 4, we're going to get 5x to the 4th. So this is the power rule, or the reverse of the power rule. So the general antiderivative for a power function is going to be to increase the exponent by 1. So if the exponent is n, right, any exponent, we're going to increase it by 1, and then we're going to divide it by that new exponent, n plus 1. And then we have a plus c. Okay, we could also just write this, since there's a 1 in front of the x, we could write this as 1 over n plus 1 times x to the n plus 1 plus c. Okay, either of these two would work, and they are the same thing. So if we look at this example, we want to find the most general antiderivative of the function. So we're finding capital F of x. So we're going to take the first term, which is 6x to the 5th. We're going to increase the exponent by 1. So instead of 5, it's going to become 6. And then we're going to divide by the new power of 6. So then we have negative 8x. Instead of to the 4th, we're going to increase it by 1. So it becomes 5. And then we divide by 5. And then negative 9x, instead of squared, we're going to increase it by 1. So cubed over 3, because that's the new exponent. And then we have plus a constant, so plus c. And then just to clean it up a little bit, we're going to divide. So this becomes x to the 6th minus 8/5 x to the 5th minus 3 x to the 3rd plus c. And you could always double check your work by finding the derivative. So if we took the derivative of this, we would have 6x to the 5th minus 8x to the 4th minus 9x squared, which is what we started with. Okay, so if we look at this example, we can see that there are radicals in the problem. So what we want to do first is change the radicals to rational exponents so that they're easier to work with when using the reverse power rule. So this becomes 3x to the 1/2 minus 2x to the 1/3. So now to find the antiderivative, we have 3x. Now instead of 1/2, we're going to increase that by 1. So we're really going to be adding 2 halves. So that's going to become 3 halves. Oops, 3 halves. And then we're going to divide by 3 halves. And then we have negative 2x. And instead of 1/3, we're going to add 1. So we're adding 3/3. So that becomes 4/3. And we're going to divide by 4/3 and then plus c. So to clean this up a little bit, we're going to actually just divide. So when we divide 3 by 3 halves, it's the same thing as multiplying 3 by 2/3. So we get 2x to the 3 halves. And then we have here 2 divided by 4/3 is really 2 times 3/4, which is 3 halves, x to the 4/3, and then plus c. So the most common way to express the relationship between a function and its antiderivative is with an integral sign with no limits of integration. So this is called an indefinite integral. So they might ask you to find the antiderivative, or they're going to ask you to find the integral. And a lot of times they don't say find the whatever, they'll just give you this symbol, and that means find the antiderivative. So antiderivative and integral are one and the same. And there's 2 types of integrals. So last class we talked about the definite integral, which is the one here on the left. And we can tell that this is a definite integral because we have limits of integration. And when we solve this, the answer that we get for a definite integral is going to be a number. And that's what we did last class. And we were finding the number of what the area was under the curve. And then here, this is a indefinite integral. And that's because we do not have limits of integration. And when we solve this, the answer that we get is going to be a function. Okay, so when we found derivatives, the derivative itself would be a function, and then the derivative at a point would give us a number. So basically, the integral that's indefinite is giving us that function. And if we put on the limits of integration, that's kind of like finding the integral like at a point almost, but it's over an interval. So two types of integrals, and we'll be able to use both types. Here's a table of indefinite integrals. So all of these pretty much are things you've seen before. If you know all the derivatives of things, these are just the backwards of that. So when we're looking at what's in the integrand, which is the thing inside the integral sign, we can see that, like for instance, the sine of x dx, that's looking at the derivative. So we're saying, okay, the derivative is sine of x, so what is the original function? Like, what gives us a derivative of sine x? And that's negative cosine x. All right, same thing here. Secant squared x, that should look familiar to you. That's the derivative of what? That's the derivative of tan. So now we're kind of working backwards. So let's look at this example. So what we can do here is we can use our properties of integrals to kind of break this up a little bit. And we don't have to, but for this example I will. So we have the integral of 4 sine x. And then because I'm dividing both of these by x, I'm going to separate this and say that this is 2x to the 5th over x minus square root of x over x, and then dx. So I can split this up because they're both being divided by x. From the properties of definite integrals from last class, we knew that we can pull out constants. So the 4 I'm going to pull out. So now I have the integral of sine x dx. I'm going to split up all these integrals because I have addition and subtraction. So plus, the 2 is going to get pulled out since it's a constant. If I simplify x to the 5th over x, that's going to give me x to the 4th dx. And then there's no constant to pull out of this one, so I won't take anything out. And then the square root of x over x is going to give me x to the negative 1/2 dx. So now I'm going to go ahead and take the antiderivative. So the antiderivative of sine x dx is negative cosine x. So I have a 4 in front, so I'm going to have negative 4 cosine x plus 2 times the antiderivative of x to the 4th. We're going to use the reverse power rule. So this becomes 1/5 x to the 5th. And then here, if I have x to the negative 1/2, if I increase the exponent by 1, that's going to give me positive 1/2. And what's in front of this is a 1, right? So I pretty much have to divide this by a half. So 1 divided by a half is going to give me 2x to the 1/2. So I can actually just multiply the 2 and the 1/5 together to make this a little bit nicer to look at. And I don't want to forget my plus c. Oops. Okay. So here again we have a indefinite integral, so we're just going to find the antiderivative. Because everything is divided by x cubed, we're going to go ahead and divide everything by x cubed. So this is going to give us x to the negative 1 plus 2x to the negative 2 minus 3x to the negative 3. When you have x to the negative 1, that's the same thing as 1 over x, and we know that that is going to be ln of x. If you try to use the reverse power rule, you're going to get an exponent of 0, and that should be kind of like a bell and whistle here that that's something weird about that, so it's going to be not, able to use the reverse power rule. So we'll have the ln, absolute value of x. We're going to increase the negative 2 by 1 to get negative 1, and then we're going to divide negative 1, so we get negative 2x to the negative 1, and then negative 3 will increase by 1 to get negative 2, and then we'll divide by negative 2, so positive 3/2 x to the negative 2, and don't forget that plus c that we're going to tack on at the end.